In this video, we will look at the 0-1 knapsack problem which is solved using dynamic programming. In the knapsack problem, we have a set of n objects. For example, let us consider we have 3 objects and a knapsack. Each of these objects have weights associated with them. The weight of each object is represented by W. So let us consider W1 as the weight of object 1, W2 as the weight of object 2, and W3 as the weight of object 3. Then we also have profits associated with each object. The profit of each object is represented by P. So let us consider P1 as the profit of object 1, P2 as the profit of object 2, and P3 as the profit of object 3. Then we have the capacity of the knapsack represented by M, that is the maximum weight the knapsack can carry. The 0-1 knapsack problem is to fill the knapsack with the objects that maximizes the total profit. This is known as the objective function. Let us consider an example. Let us consider we have 3 objects. The weight W1 of object 1 is 2 and the profit P1 of object 1 is 1. The weight W2 of object 2 is 3 and the profit P2 of object 2 is 2. And the weight W3 of object 3 is 4 and the profit of object 3 is 5. All the weights and profits are considered to be positive values. Then let us consider the capacity M of the knapsack is 6. Now the 0-1 knapsack problem is to fill the knapsack with the whole of the object or the object is not used to fill the knapsack. This is the reason the problem is called 0-1 knapsack. If the object is not used to fill the knapsack, then the solution x is 0. And if the object is used to fill the knapsack, then the solution x is 1. The objects that are used to fill the knapsack should maximize the total profit. To do this, we can fill the knapsack with any of the objects, but the total weight of the objects in the knapsack cannot exceed the capacity of the knapsack. This is the constraint of the knapsack problem. Now using dynamic programming, the solution to the 0-1 knapsack problem can be obtained by making a sequence of decisions on the solution variables x1, x2, so on till xn. A decision on variable xi involves determining which value 0 or 1 is to be assigned. If the object is included in the knapsack, then the solution xi is 1, and if the object is not included in the knapsack, then the solution xi is 0. So to solve this problem using dynamic programming, we use ordered set Si where each member is a pair of profit and weight. Initially the set S0 contains a pair 0, 0. That means there is no weight in the knapsack and no profit is earned. Then the first object with profit 1 and weight 2 is included by creating a set S01 and including the pair P1 W1 of the first object, which is 1, 2 in the knapsack. The set S01 contains a pair which is the result of adding the pair P1 W1, which is 1, 2 to the pair 0, 0 of set S0. That is adding profit 1 to profit 0 and adding weight 2 to weight 0. Then S1 is computed by merging the set S0 and S01. So set S1 will contain 2 pairs of profit and weight, that is 0, 0 and 1, 2. Now observe that the first pair in the set S1 is 0, 0, which means first object is not included, and the second pair in S1, that is 1, 2 means first object is included in the knapsack. So in dynamic programming approach, we compute sets containing pairs of profit and weights by considering all the possibilities of including the objects and not including the objects, and then at the end select the best possible solution that will be optimal. So here we have set S1 containing 2 pairs of profit and weight, that is 0, 0 signifying object 1 is not included and 1, 2 signifying object 1 is included. Then to set S1, we add the second object with profit 2 and weight 3 by creating a set S11 and including the pair P2 W2 of the second object, which is 2, 3. So the S11 will contain the pairs which is the result of adding the pair P2 W2, which is 2, 3 to every pair of set S1. So the first pair of set S11 will be 2, 3 plus 0, 0, which is 2 plus 0 is 2 and 3 plus 0 is 3. So the first pair is 2, 3. Then the next pair of the set S11 will be 2, 3 plus 1, 2, which is 2 plus 1 is 3 and 3 plus 2 is 5. So the second pair is 3, 5. Then the set S2 is computed by merging the set S1 and S11. So the set S2 will contain the pairs 0, 0 and 1, 1 from set S1 and the pairs 2, 3 and 3, 5 from set S11. So if you observe, the first pair 0, 0 of set S2 means object 1 and object 2 is not included. Then the second pair 1, 2 means only object 1 is included and profit is 1 and weight is 2. Then the third pair 2, 3 means only object 2 is included and the profit is 2 and weight is 3. And the fourth pair 3, 5 means both object 1 and object 2 is included and the profit is 3 and weight is 5. So this way we consider all the possibilities of including and not including the objects in the knapsack. Now after computing the sets S of pairs of profit and weights, we need to check if the weights in the pairs computed exceeds the capacity M of the knapsack. That is, if the weight W in the pair is greater than M, then purge the pair or simply discard the pair from the set. So at this stage in the set S2, the first pair is 0, 0 where weight is 0, which is less than 6, which is the capacity of the knapsack. So this pair is part of the set. Then the second pair is 1, 2 where weight is 2 and is less than 6, which is the capacity of the knapsack. So this pair is also part of the set. In the same way, pairs 2, 3 and 3, 5 has weights 3 and 5, which are less than 6, that is the capacity of the knapsack. So these pairs are part of set S2. Then we also need to compare the profits and weights of every two subsequent pairs and decide which pair to purge or discard. For example, the profit of first pair is 0 and profit of second pair is 1. So profit is increasing as well as the weight of first pair is 0 and weight of second pair is 2. So even the weight is increasing. Therefore the pair 0, 0 is part of the set S2. Then we need to compare the next two pairs. The profit of the second pair is 1 and profit of the third pair is 2. So profit is increasing as well as the weight of second pair is 2 and weight of the third pair is 3. So even the weight is increasing. Therefore the pair 1, 2 is also part of the set S2. In the same way, we need to compare the next two pairs. The profit of the third pair is 2 and the profit of the fourth pair is 3. So profit is increasing as well as the weight of the third pair is 3 and the weight of the fourth pair is 5. So even the weight is increasing. Therefore, the pair 2, 3 is also part of the set S2. So at this stage, the weights of all the pairs are less than the capacity M of the knapsack and all the pairs are having increasing profits and increasing weights. So none of the pairs are discarded. Then to set S2, we add the third object with profit 5 and weight 4 by creating a set S21 and including the pair P3 and W3 of the third object, which is 5, 4. So the set S21 will contain the pairs which is the result of adding the pair P3 W3, which is 5, 4 to every pair of set S2. So the first pair of set S21 will be 5 comma 4 plus 0 comma 0, which is 5 plus 0 is 5 and 4 plus 0 is 4. So the first pair is 5 comma 4. Then the next pair of the set S21 will be 5 comma 4 plus 1 comma 2, which is 5 plus 1 is 6 and 4 plus 2 is also 6. So the second pair is 6 comma 6. Then the next pair of the set S21 will be 5 comma 4 plus 2 comma 3, which is 5 plus 2 is 7 and 4 plus 3 is also 7. So the third pair is 7 comma 7. And the next pair of set S21 will be 5 comma 4 plus 3 comma 5, which is 5 plus 3 is 8 and 4 plus 5 is 9. So the fourth pair is 8 comma 9. Then the set S3 is computed by merging the set S2 and S21. So the set S3 will contain the pairs 0 comma 0, 1 comma 2, 2 comma 3 and 3 comma 5 from set S2, and the pairs 5 comma 4, 6 comma 6, 7 comma 7 and 8 comma 9 from the set S21. Now after computing the set S3 of the pairs profit and weights, we need to check if the weight in the pairs computed exceeds the capacity M of the knapsack. That is, if the weight W in a pair is greater than M, then purge the pair or simply discard the pair from the set. So in set S3, the last pair is 8 comma 9, where weight is 9 and is greater than the capacity 6 of the knapsack. So this pair 8 comma 9 is discarded. Then the second last pair is 7 comma 7, where weight is 7 and is greater than capacity 6 of the knapsack. So even this pair 7 comma 7 is discarded. Now the weights of all the other pairs in set S3 are less than or equal to the capacity 6 of the knapsack. Therefore these pairs are part of the set S3. Then we also need to compare the profits and weights of every two subsequent pairs and decide which pair to purge or discard. For example, the profit of the first pair is 0 and profit of the second pair is 1. So profit is increasing as well as the weight of the first pair is 0 and weight of the second pair is 2. So even the weight is increasing. Therefore the pair 0, 0 is part of the set S3. Then we need to compare the next two pairs, that is the pair 1, 2 and 2, 3. The profit of the pair 1, 2 is 1 and the profit of the pair 2, 3 is 2. So the profit is increasing as well as the weight of the pair 1, 2 is 2 and the weight of the pair 2, 3 is 3. So even the weight is increasing. Therefore the pair 1, 2 is part of the set S3. In the same way, we need to compare the next two pairs 2, 3 and 3, 5. The profit of the pairs 2, 3 is 2 and the profit of the pair 3, 5 is 3. So profit is increasing as well as the weight of the pair 2, 3 is 3 and weight of the pair 3, 5 is 5. So even the weight is increasing. Therefore the pair 2, 3 is part of the set S3. Then we need to compare the next two pairs, that is pair 3, 5 and 5, 4. The profit of pair 3, 5 is 3 and the profit of the pair 5, 4 is 5. So profit is increasing. But the weight of the pair 3, 5 is 5 and the weight of the pair 5, 4 is 4. So the weight is decreasing. Therefore the pair 3, 5, which is having less profit and more weight, when compared to the pair 5, 4, which is having more profit and less weight, is purged or discarded. This is known as purging rule or dominance rule. So if the set Si contains two pairs Pj, Wj and Pk, Wk, where Pj is less than equal to Pk and Wj is greater than equal to Wk, then the pair Pj, Wj is purged or discarded. And we say that the pair Pk, Wk dominates the pair Pj, Wj. So since the pair Pk, Wk dominates the pair Pj, Wj, the pair Pj, Wj is purged. and the pair pk comma wk is the part of the set Si. So here among the pairs 3 comma 5 and 5 comma 4, the profit is increasing and the weight is decreasing. Therefore the pair 5 comma 4 dominates the pair 3 comma 5 and pair 3 comma 5 is discarded. Now after this step, we again need to apply the dominance rule between the previous and the next pair. So here among the pairs 2 comma 3 and 5 comma 4, the profit is increasing as well as the weight is increasing. Therefore both the pairs are part of set S3. Then among the pairs 5 comma 4 and 6 comma 6, the profit is increasing as well as the weight is increasing. Therefore both the pairs are part of the set S3. So at this stage the weights of all the remaining pairs are less than the capacity M of the knapsack, and all the remaining pairs are having increasing profits and increasing weights. Now we have considered all the possibilities of including or not including all the three objects, and set S3 is the final set. Then the last pair 6 comma 6 in set S3, where profit is 6, will give us the maximum profit earned, which is 6. Then we need to perform traceback to get the solution of which object is included and which object is not included. So we need to trace back how we got the pair 6 comma 6 in set S3. We got the pair 6 comma 6 from set S21. Now the pair 6 comma 6 is in set S21 because of adding the pair P3 W3, which is 5 comma 4, to set S2. That means the pair P3 W3 representing object 3 is included. Therefore the solution X3 will be 1. Then to which pair in set S2 we added the pair P3 W3, that is 5 comma 4, representing object 3, to get 6 comma 6. We added the pair 5 comma 4 to the pair 1 comma 2 in set S2 to get 6 comma 6. Now this is same as subtracting the pair 5 comma 4, which is included from the pair 6 comma 6, which is 6 minus 5 comma 6 minus 4, that will give us 1 comma 2. So now we need to trace back how we got the pair 1 comma 2 in set S2. We got the pair 1 comma 2 from set S1. That means the pair P2W2 representing object 2 is not included. Therefore the solution X2 will be 0. Remember, the set S1 contains pairs not including the pair P2W2 representing object 2, and the set S11 contains the pairs including the pair P2W2 representing object 2. Therefore, since the pair 1 comma 2 is in set S1, so the object 2 is not included and the solution X2 is 0. Then we need to trace back how we got the pair 1 comma 2 in set S1. We got the pair 1 comma 2 from set S01. Now the pair 1 comma 2 is in set S01 because of adding the pair P1W1, which is 1 comma 2, to set S0. That means the pair P1W1 representing object 1 is included. Therefore the solution X1 will be 1. So the maximum profit earned is 6, and tracing back the solution we get X1 as 1, X2 as 0 and X3 as 1. That means object 1 is included, object 2 is not included, and object 3 is included in the knapsack to earn maximum profit of 6. So to summarize, in the 0-1 knapsack problem, we have set of n objects. Each of the objects have profit P and weight W associated with them. The knapsack has capacity M, that is the maximum weight the knapsack can carry. The 0-1 knapsack problem is to fill the knapsack with the objects that maximizes the total profit, subject to the condition that sum of the weights of the objects included in the knapsack is less than equal to capacity M of the knapsack. If the object is included in the knapsack, then the solution Xi is 1. otherwise the solution xi is 0. The problem of 0-1 knapsack is solved using dynamic programming approach. In dynamic programming, we use ordered sets Si where each member of the set is a pair of profit and weight. The set Si represents the possible states resulting from the decision sequences of Xi whether an object is included or not included in the knapsack. The state refers to the pair Pj-Wj where Wj is the weight of the object included in the knapsack and Pj is the corresponding profit. The initial set S0 contains a pair 0, 0. The set Si1 is computed by adding the pair Pi-Wi representing object I to each pair of the set Si. Then the set Si plus 1 is computed by merging the sets Si and Si1 along with purging or discarding the pairs whose weights are greater than the capacity M of the knapsack, as well as applying the dominance rule to purge the pairs. Then the profit in the last pair in the set Sn gives the maximum profit earned. The solutions Xi are computed by tracing back the pairs P, W generated. Now, since the sets Si contains pairs of profits and weights representing all the possibilities, therefore the time taken to compute the set Si will be 2 power n, where n is the number of objects. Hence, the time complexity is O of 2 power n or exponential. Now, the time complexity seems to be very large even for small values of n. But in practice, this problem can be solved in reasonable amount of time because as the sets Si are computed, the pairs are purged whose weights exceeds the capacity M of the knapsack, and pairs are also purged according to the dominance rule. Therefore, practically, this problem can be solved in O of n square times. So this is all about the 0-1 knapsack problem solved using the dynamic programming approach.